Okay, hi everyone. Today we have Leo as our speaker, and he will introduce his talk about design and formally verify post-quantum cryptography. Let's welcome our speaker.
Okay, great. Yeah, thanks for the introduction. So in this talk, I'll talk about the design and formally verify post-quantum crypto. In the past 2 years, due to the pandemic, we work from home. Like we use a room to replace the normal meeting rooms, and we use instant message such as WhatsApp and email to talk to each other. Also, we shop online on Amazon for grocery and other things. All the communication happen here, whether it happens in the application or on online shopping, are encrypted to ensure your private information is not leaking to others. So other than these basic schemes, like cryptography today can do much more than that. For instance, using secure multi-party computation, we can compute arbitrary function among multiple parties without leaking each party's inputs. Secondly, using identity-based encryption or like attribute-based encryption, we can provide fine-grained access control over encrypted data. At last, like we can use homomorphic encryption to do this privacy-preserving machine learning. So cryptography today can do much more than just the basic needs. And these crypto systems are based on like various mathematical structures. For instance, in public key encryption, we can use different mathematical systems to instantiate it. One example is RSA. So RSA is based on the harness of factoring. The factory problem actually can be broken by the quantum computers with enough qubits using Shor algorithm. So like in summary, the cryptographic assumption that underlie today's internet can potentially be broken by quantum computers with enough qubits. In the past several years, there has been significant progress in the physical realization of quantum computers. So IBM plans to have 1,000 qubits computer ready by 2023. So they have a few months left. And Google has already built a quantum computer with 53 qubits. Recently, there is an article in Nature saying that quantum supremacy has been achieved using a special kind of quantum computer. So quantum supremacy means there exists a problem that can be solved by quantum computers, but cannot be solved by classical computers within any feasible amount of time. Considering the threat posed by quantum computers, this initialized a post-quantum crypto standardization process in 2016. And similar standardization effort happened in Europe as well. Google experimented the post-quantum key exchange protocol in its browser. It shows acceptable performance in comparison with the current in-use key exchange protocols. So in addition to these basic crypto primitives, such as encryption and signature, we also designed some other more advanced post-quantum crypto systems. So the urgent issue and one of my research interests is to design crypto systems that are secure against quantum computers. For this topic, I have developed fine-grained access control system and secure computation system over encrypted data from post-quantum assumptions. In the past decade, cryptography is becoming more practical and closer to our daily life. So cryptography provides various functionalities that can be used in different scenarios. For instance, threshold cryptography has been deployed in the blockchain community to enhance the validity of transaction. So this starts investigating the security of current in-use threshold crypto system. Secure multi-party computation has been deployed in many places, such as preventing tax fraud and satellite collision. A cryptocurrency company called Zcash is using their knowledge proof to secure the transactions. The point I want to make here is that beyond the basic schemes such as encryption and signature, the advanced cryptography is becoming more and more practical. But as Uncle Ben said, with great functionality comes with great complexity. As the crypto systems become more complicated, their security proofs are becoming more subtle, lengthy, and tedious. And the only insurance we have right now is the cryptographers who read the papers, but they usually just give the detail of the proof. So this proof may be error-prone and flawed. And the field of cryptography is approaching a crisis of rigor, and we are essentially generating more proofs than we can carefully verify. For instance, as I said before, Zcash is a blockchain company whose main value comes from its privacy properties. And these privacy properties are achieved using some special kind of zero-knowledge proof scheme. And Zcash was deployed based on this specific cryptographic scheme. And everything was fine until 4 years later. A cryptographer came along and found a flaw in the secured proof of the Zk scheme. And this flaw was reported directly to the Zcash developers, who then fixed it. But if a hacker knew about the flaw, they could have created Zcash out of the thin air, and this would crash the entire Zcash ecosystem. So now the fact that the flaw existed for so long isn't the fault of any specific cryptographer. These papers are now hard to read and write. There are only so many cryptographers who are capable to check the proof. So how do we protect ourselves against the security flaw in papers? We can use formal verification to rescue us out of the crisis here. So formal verification could generate machine-checked proof for crypto systems we want. And this can help us find security flaws in the papers and thus enhance our confidence in the crypto systems we use. The second urgent issue of my research interest is to formally verify cryptography. In this talk, I'll first talk about how to design post-quantum cryptography. In this part, I'll show how to construct a more efficient attribute-based encryption scheme from a post-quantum assumption. So attribute-based encryption scheme is a crypto primitive that provides access control over encrypted data. Let me first motivate this primitive using an example. So suppose my PhD advisor, Elaine, she's working on a bunch of deadlines as last night. Yeah, so she has a grant proposal due in 1 week, a conference paper due in 3 days. She also needs to write a recommendation letter for me. So she needs to concentrate on these deadlines and cannot be distracted from her emails. So what will she do? She can set up an AI responder to handle her encrypted email before these deadlines. So suppose I'm sending a funny dog picture to Elaine. The metadata of this email contains a subject, this funny dog picture, and the sender's email address. This metadata is public. I'll use X to denote it. The private part of this email is the content of the email. In this example, is this sentence and also the picture. So I'll use M for the actual email message. In this example, I'll just assume the subject of the email is in the public metadata. And this assumption will make this example more interesting. So Elaine will impose some filter rule for her email. And this rule depends on the metadata of the email, which are the subject and the sender's email address. She encodes this rule in a security token, and then put the security token in the responder. For instance, if the subject contains picture, then the responder can decrypt the email and then reply based on the contents. For instance, like the responder can reply my email like this. This is a funny dog picture, but you should spend more time on your research. If this email is from a special person, say Santosh on a grant proposal, then the responder cannot decrypt and will forward the email to Elaine. If this email is coming from a student and contains homework, then the responder can decrypt it and then uses advanced AI technology to reply it immediately. And this immediate response could help Elaine in her course evaluation. So APE was first proposed by Sahai and Waters in 2005 to abstract something out of the example, and also to make things a little bit more formally. The syntax of the APE is the following. So Elaine will first set up the system by running the setup algorithm. She obtains a public key and a master key after running the setup algorithm. She then uses a master secret key to generate a token for her email rules. So the email rules are denoted by this database D, and then she can put this security token in the responder. This database D here contains all the information for the email rule, such as all students' name, for the third rule of the previous slide. When someone wants to send an encrypted email to Elaine, he encrypts his email using the public key and public metadata X. So the responder can decrypt and auto-respond if the filter rule on the metadata is false. Otherwise, it cannot decrypt and will have to forward the encrypted email to Elaine. This otherwise operation also defines the security of the email, like the responder cannot learn anything about the encrypted email if it cannot decrypt. So that's the syntax of ABE. And this response rule can be quite complicated. For instance, to tell whether this email is sent from a student, the whole list of students' names should be in this database theme. The responder can use a prefix tree to determine if the sender is a student or not. This prefix tree is complicated and contains a lot of information. But to determine the sender's information for an email only takes a parse from root to leaf. Therefore, although the size of the tree can be quite large, the computation for each email could be quite efficient. The prior work, BGG plus 14, it shows how to construct the AB for circuits. If we want to use the result for the responder example, then we need to convert this like complicated prefix tree into a circuit, and the size of the circuit will depend on the size of the tree. For each email, the responder needs to run this large circuit to determine the status of the email, and this will significantly slow the speed of the responder, since the prefix tree can be very large. In our work, we overcome this efficiency issue. We construct an AB scheme that can deal with this example more efficiently. In our construction, the response time for each email only depends on the length of the exact path from root to leaf. So this prefix tree can be treated as a special case of the RAN computing model. In RAN, the database is stored in the memory. So I input one entry from the database and the register. The CPU circuit will do some internal process and then update the register. Then the CPU can read the next entry of the database depending on the current status of the CPU, and then do the process again. And this procedure could happen many times until the CPU is terminated. Our result also works for general RAM program. The decryption time of our construction only depends on the actual runtime of the RAM program. If you want to use prior work for the RAM programs, then the decryption time depends on the size of the database, as you first need to convert the RAM program into a circuit. For instance, if the RAM program is a binary search, then our decryption time will only depend on the logarithmic size of the database. And this is an exponential improvement compared with prior work. Now we are diving into the technical detail of our construction. I'll first talk about some lattice preliminaries. Then I'll explain the main idea of constructing AB scheme for circuit for lattices, which is a component of our AB for RANs construction. And after that, I'll move on to construct the AB scheme for read-only RANs. Okay, yeah. So what is a lattice? It's a discrete subgroup of the n-dimensional real numbers. So here, n is a dimension of the lattice. For instance, this picture is a two-dimensional lattice. The green points are in this lattice. In summary, there are 4 nice properties of lattice. First one, like the computation over lattice is efficient. The computation is basically a matrix vector operation or polynomial multiplication, so it's linear and parallel. Second, the hardness assumption based on lattices are conjectured to be quantum secure so far. And the third one is that the crypto system based on lattices can have their security from worst case assumptions. And this requirement is weaker than the average case assumption we usually ask for cryptography. At last, lattice provides a solution to some holy grail problems such as homomorphic encryption and obfuscation. The hardness assumption, the post-quantum one we're going to use in this talk, is a learning with error assumption introduced by Regevos in 2005. So there are 3 parameters in this assumption: the lattice dimension n, the modulus q, and the error distribution. And the decisional LW assumption is to ask you to distinguish matrix A and vector B from uniformly random matrix A and vector U. So here the dimension of this A is n by m. This is a short fat matrix chosen from the random distribution. And the vector B is computed as S times A plus E, where S is an n-dimensional random vector and E is an m-dimensional vector sample from the L distribution. If you don't have the noise, then probably you can solve the equation using Gaussian elimination. So researchers have shown that LW problem is hard by giving reduction from worst case lattice problem to LW problem. So that's the prelim for lattice-based for lattices. Let me right now explain the main idea for constructing AB scheme for circuit for lattices. Let's say we have an encryption scheme that takes as input the public key, the metadata X, and the message M. What we will do in the decryption is the following. So I'm going to compute on the ciphertext for this policy function and attribute X. This policy function is a circuit we care about in the AB scheme. In other words, I'll come up with a way to convert the ciphertext under PK into another ciphertext under a different public key, this PK sub F. And this PK sub F is a public key depending only on the function F. And when I'm doing this evaluation for the ciphertext, it automatically also computes the ciphertext on the attributes X for the same function F. And this is the first step of the decryption, this CT to CT sub F of X part. This is a public evaluation. Everyone can do it. I'm not doing anything to the message. It stays the same. Either the decryptor can decrypt it or the decryptor cannot. So it's not related to the evaluation part. Let's forget about it. Then I can give you a token for this function F. Once you put them together, then you can recover the message M if F of X equals 0. So the decryption consists of these 2 parts. The first one is a large public evaluation that everyone can do it. And this is a ciphertext evaluation. Then with the security token, you can recover the message, and that's how it works. So there are basically 3 components in the ABE construction. The first one is like, how do I go from one public key to another public key for function F? So that's the PK to PK sub F part. And this part is used in the key generation. The second one is, how do I compute the ciphertext for the function F and the input X? So this CT to CT F of X part. The third one is, what is the magic security token that help you recover the message M? So that's the 3 components for AB construction. Let's talk about the first component, the public key evaluation. And this part is about evaluating the public key for any circuit. So suppose F here is a circuit we care about in the AB scheme. So for each input wire of the circuit, we assign a matrix, say this A1 to it. I'll use different color squares for different matrices. They are in the public key. In this paper, BGG plus 14, they show a deterministic way to evaluate these matrices for any circuits. We're not going to discuss the detail of the evaluation method. So just remember that if the matrix for each input wire is fixed, then we can compute the matrix for the output wire of the circuit. And that's how the first component is done, this evaluation of public key. The second component is a ciphertext evaluation for function F and input X. Let's say this X1 to X4 are the input to the function F. For each input Xi, we compute this S times AI plus Xig plus error, and we call this the LW encoding of Xi. So here, this matrix G is a gadget matrix that has some nice properties for evaluation. So each circle here is an LW encoding of the input xi using the same vector s, but different error vectors. I'll use different different color circles to represent the LW encoding for different inputs. So in this same paper, they show that they can also evaluate the inputs encoding to get an LW encoding of the output f of x, which uses the same vector s. Let's see in this slide and the next about the mathematics behind these squares and circles. The first component, the public key evaluation, happens in the key generation. So on input the matrices for each input wire, we can deterministically compute the output matrix for the function f. And then we can use the master secret key to generate the security token T sub f. So T sub f is basically a small vector R satisfying A times A sub f times R equals U. And this is the third component of the AB construction. This matrix A1 to A4 and vector U are all in public parameters. The encryption of the message M using attribute X and public key contains an LW encoding of attribute X and the encryption of the message. The LW encoding of attribute X are these circles, and they are generated using the same vector S but different error vectors. Here, for instance, the LW encoding of X1 is generated using matrix A1, which is the first input on the left-hand side. I ignore the error vectors here. The encryption of the message is the CT sub M part, which is a one-dimensional LW instance plus a message. In the decryption, the first step is to evaluate this LW encoding for function f and input x. The result of the evaluation is an LW encoding of the result f of x using the same vector s. And this is the first step in the decryption, the large public evaluation. The second step of the decryption is to take the security token T sub f to recover the message M. And the simplified equation of the second step is something like this. So in this equation, if f of x equals 0, then by the property of the security token, we can have s times a sub f times r equals s times u. And this cancels out the SU part in the encryption of the message. Then the message can be recovered then. Going forward, I won't show this equation anymore. I'll just take these circles and squares abstractly. Remember, the squares are used to denote the matrices, and the circles are the LW encoding using the matrices. So just take my word for it. There exists a way to algebraically instantiate the circles and squares. The components of constructing AB scheme are having the evaluation method for both the public key and the ciphertext. The magic security token is basically a pre-image of some vector in the public key. And this process is simple using the master secret key. The complicated part is to have the evaluation method for the RAMs. Here I'll show how to do it for read-only RAMs. So in the RAM setting, this database D is in the public, is in the key generation. So the memory is encoded using the database D and public key. For instance, the blue square of X1 can be unfolded as A1 plus X1G. In the RAM evaluation, the CPU needs to read one entry from the memory, but this exact read address is not known during the key generation, since the input to the RAM program is part of the ciphertext. More specifically, if we let these two inputs to be like the wire of the register, then the leftmost one be the wire of the memory read, then we cannot run the public key evaluation for the CPU circuit, since we don't know which square to pick from the memory. So to solve this issue, we use a building block called 2-to-1 recoding. So with a master secret key, we can generate some useful triangles, and these triangles can be converted something to other things we want. For instance, we can generate a triangle from a gray square of I, a blue square of X, to an orange square of X. So somehow magically, this triangle can be used to convert the LW encoding of I, the LW encoding of X, to the LW encoding of X in the orange color. So it converts two LW encoding into one LW encoding. That's why it's called 2-to-1 recoding. But if you want to use this triangle to convert something else, such as like this gray square of J, then it's not going to work. You'll just get some random stuff in the end. So how would this recoding method help us? So suppose a key generator, he runs the CPU for the first time, and then obtain a gray square. So the gray square denotes the read address for the next step. But we don't know which index of the memory to read yet. So the key generator, he can actually sample a fresh square, say this orange square, for the read value of the second run of the CPU. The orange square can be plugged into the CPU circuit for the second run, then he can obtain a dark square for the read address of the third run. And in the meantime, the key generator can compute a blue triangle for the first index of the memory using the master secret key. And this triangle can compute, and this triangle will convert this like gray square of 1, a blue square of x1 to an orange square of x1. And this triangle basically converts the first location of the memory to the input of the CPU. Sequentially, the key generator can generate a red triangle for the second index of the memory and a green triangle for the third index, so on and so forth. So the security token for the second step will contain all these triangles. And these triangles are the bridge between the memory contents and the CPU inputs. So how do this triangle help in the decryption? So suppose the decryptor runs the CPU for the first time, and he will obtain a gray square of say the read address is 4. Since the read address is public, he can just pick the corresponding circle and square, and with the help of this blue triangle, he can get the orange square of x4, and then this orange square x4 can be plugged into the CPU circuit to get another run of the CPU. But if he picks the wrong color, then he will just get some random stuff and cannot proceed with the RAM evaluation. And this is guaranteed by the property of the 2-to-1 recoding, as I mentioned before. And these triangles achieve both the recoding part and also the authentication functionality, and prevents the decryptor from learning anything about the message he cannot decrypt. And that's basically the intuition, like how we achieve security for our AB construction. So in summary, the key insights we have here is like we can generate the secret key prior to the RAM evaluation, and we can make it independent of the read address. So in that sense, we can then run the decryption as a RAM program, and we have the efficiency improvement for decryption algorithm. The runtime of it only depends on the actual runtime of the RAM program. And we achieve this at the cost of larger secret keys. But this like the generation of the secret key is just a one-time thing. So the cost can be amortized over many decryption using the same key. And there are some other detail I didn't cover in this talk, such as like how to write to the memory and what is the security proof like from LW assumption. If you are interested in that, you can please take a look at our paper. Okay, so that's the first part of my talk. The second part of this talk is about the formal verification of cryptography. So there are like two approaches in the formal verification of cryptography. The first one is a symbolic approach introduced by Donovan and Yao in 1983. So the symbolic model is an abstract model for analyzing cryptographic protocols. The message sent in these protocols are represented symbolically as terms. So these terms are atomic data. Cryptographic primitives used by these protocols are modeled as black box function over these terms. And this modeling makes it very good at automation. But one drawback of this approach is that some subtle soundness issues are not captured in this model. For instance, the public key encryption is treated as an ideal box in the symbolic model. And in this modeling, the encryption of anything is secure. But in crypto, if you use a public key to encrypt the secret key, then this encryption most likely is not secure. And it leaks information about the secret key. And this also shows that the proofs generated in the symbolic approach is somehow different from the on-paper proof. The second approach is the computational approach. So in this computational approach, the message, they are treated as bit streams. So they are not atomic data. And cryptographic primitives are just the probabilistic algorithms over bit stream. So this gives us the freedom to reason about the security of both primitive and the protocols. One drawback of this approach is that it usually require user interaction in the verification process. In some cases, it needs hint from the user to complete the verification process. But one good benefit one can get from the computational approach is that it can generate like the on-paper proof. Since these tools are mainly used by cryptographers, I would consider this as a benefit of the computational approach. And the tools from these two approaches have been used in a range of real-world cryptographic mechanisms, such as TLS, Signal, and AWS key management. So it would be better to combine these two approaches, like to have a system that can do this sort of automatic reasoning of crypto in the computational model. And also we want to the feature of this closed on-paper proof. And this ensures that the abstraction we are doing in the system is on the same level of what cryptographers do on paper. And this would somehow promote the use of our tool to cryptographers. So in our AutoLWE paper, we combine these symbolic and computational approaches. So our AutoLWE system is the first verification tool for lattice-based crypto. We verify some list post-quantum candidate prototypes, and the verification time is very short. It can be done in less than 3 seconds. In the following, let me use an example to show how the AutoLWE system works. The lattices are just about matrices and vectors. So in our system, we don't care about each entry of a matrix. The thing we care about for a matrix are the row and column dimensions. So we use this matrix RC to denote an R by C matrix. So recall that the learning with error assumption is to distinguish a random M by N matrix and S times A plus E from a random vector U. Using the syntax we just defined, the LW assumption we can encode in our system can be something like this. So the first bullet will describe that A is a random M by N matrix, and S is an M by 1 vector, and E is an M-dimensional vector. And the adversary on input this A transpose of S times A plus the error vector will output a single bit. And the second bullet describe how the random distribution is generated. So here, this vector U is an M-dimensional random vector. The adversary needs to distinguish these two distributions. So that's how we encode LWE in AutoLWE system. A running example of our AutoLWE system is a dual Regevos PKE scheme proposed by Gentry, Piker, and Kontanansen in 2008. So in this scheme, the public key is matrix A and vector V, where this vector V equals A times R, and this red R is a secret key, it's a short vector. The ciphertext will contain 2 parts. The first part is an LW instance, this SA plus E. The second part, the SV plus error plus message, is a one-dimensional LW instance within the same vector S. And we say this PKE scheme is secure if the adversary cannot distinguish an encryption of bit 0 from an encryption of bit 1. So that's how we define the security of the PKE scheme. Okay, so let's first see how we can describe the security goal formally on paper. We can write a security gain something like this. The first and second line describe like how the public key A and V are generated. The rest line describe how the ciphertext is generated for randomly chosen bit B. And input the public key A and V and the ciphertext C0 and C1. The adversary needs to output his guess bit B prime for the random bit B. On the right-hand side, we encode the security of dual rogress PK scheme in the AutoLWE system. So here it says like this A is a random n by m matrix, and U equals A times R, and this matches how the public key is generated on the paper. The other line shows how the ciphertext is computed for random bit B in the same way as on paper. So the point I want to make for this slide is that the security goal in AutoLWE is very, very similar to its counterparts on paper. So how can we use the LW assumption to do part of the proof? It's actually quite simple. So this code describes the initial security goal. If you want to plug in the LW assumption in the ciphertext, the security gain G can be rewritten into another security gain G prime, where only the ciphertext is changed. And this rewrite is done by a single line of code, this assumption decisional LWE. And the security loss here is bounded by the hardness of the LW assumption. So that's essentially how the high-level rewrite happens. We certainly need some other rewrites for different lemmas to finish the proof, such as leftover hash lemma. So now let's look under the hood to see how we design the system. So in order to apply the assumptions such as LWE, the security gain is defined for symbolic adversary, this ADV. And the first thing we're going to do is to factor the security gain into two parts. The first part generates the LW instance, and the second part, called the simulator, will take the symbolic adversary and the LW instance, and then output the guess bit B. When the rewrite happens, the simulator replaces the input from the first part with uniformly random A and U. Then we can unfold the simulator to get the security gain G prime. Where here this ciphertext is generated using the random values instead of that in the original security gain. And given we can do this like factoring step, the techniques for applying the assumption is highly automatic and high level. And therefore the resulting proof scripts output by the AutoLWE system closely resemble their on-paper proofs. So now the question is that, how can we do this factoring? So we need to rewrite the security gain G into three parts. The first part is a G sample, which samples the LW instance. Then we create a net binding that binds the LW instance with a public variable, this PV. And this PV will be the input to the simulator. Then the simulator will take this PV and simulate the whole security gain. For this simulator to be well formed, for this simulator to be well formed, the expression inside the simulator can be written in this PV and any variable generated inside the simulator. And we need to use a symbolic tool to check the well-formedness of the simulator. So I won't have time to go over how what is the design of the symbolic checker in this talk. So like to summarize our contribution of this talk, our AutoLWE system is the first verification tool for lattice-based cryptography. It is a combination of symbolic and computational approaches. It's semi-automatic and can finish the verification in pretty short time. We will verify like two public key encryption scheme, one identity-based encryption scheme, one hierarchical identity-based encryption scheme, and an interproduct encryption scheme. And we use Alcamo to mechanize a proof. I want to emphasize one point here, like you can certainly encode the lattice operation in other formal method systems such as encrypt. But the abstraction we did in AutoLWE is at the same level of what cryptographers did on paper. So the scripts generated by AutoLWE are easier to understand for cryptographers. The AutoLWE system, like it only formalized a crypto system built on a post-quantum assumption, but it didn't provide any reasoning about this like quantum adversaries. And to overcome this issue, we built another system called EasyPQC based on EasyCrypt. So we are among the first to formalize crypto systems against the quantum adversaries. And we add some syntax and logic in the EasyCrypt system to enable it to reason about the quantum behavior. In our EasyPQC system, we formalize some list of PQC candidates. And interestingly, we found a bug. In one of the example we started in the EasyPQC system, and also we fixed it. Yeah, so in addition to the project mentioned in this talk, I also did some other work in the field of cryptography and formal verification. For cryptography, I show how to construct a secure computation scheme and decentralized access control scheme over encrypted data. For the formal methods part with my wonderful PO collaborators, we also construct a formalizing system based on the COC to reason about cryptographic protocols. Recently, I started working with the hardware guys, accelerating lattice-based crypto, also including homomorphic encryption. The last part of my talk is about ongoing and future work. My first research goal is to make this post-quantum crypto system more efficient in the real world. And we can tackle this goal via three approaches. So like in theory, we can optimize the current crypto systems for smaller size of representation and faster and more efficient computation of the algorithms. And this will require us to explore the mathematical structure of lattices. For the implementation part, if you have an advanced crypto system with desirable parameters, then we can try like software optimization tricks and also use better compiler to get faster software implementation. And last, if the software implementation is still not desirable like that for the homomorphic encryption, we can then design a specialized hardware for it, like the FPGA or ASIC to achieve like better improvements. So that's the first, that's my first research goal. The second goal is to have this end-to-end verification of cryptography. So here, end-to-end means formal verification is used in the research, implementation, and deployment phase of crypto systems. In the research part, the goal is to check if there are subtle flaws in the security proof, and that's the current focus on my research. In the implementation part, these high-level designs are then fleshed out with like concrete functional details, such as data format, session state, and the programming interfaces. So to reap the benefits of design-level security guarantees, the implementation must be an accurate translation of the design. And this means that it must be functionally correct. Moreover, to meet this like practical deployment requirement, this implementation must be also efficient. So however, the performance demands will usually drive the cryptographic code into extreme contortions that make functional correctness difficult to achieve. The last phase is a deployment. Although this like design level security can rule out large classes of attacks, so this guarantee are like proven in a model that idealizes attackers' interfaces with the underlying cryptographic algorithms. For instance, the implementation must also account for these low-level threats that are absent in the design level, such as the side channel attacks. Thanks to my wonderful collaborators, and thank you for attention. Yeah, I'm happy to take any questions.
Yeah, thank you, Leo. And if anyone has any questions, please feel free to either unmute yourself or just type in the chat. Okay, maybe Leo, can we go to slide 51? I think I wanted to hear a little
51.
about. Yeah. Oh, sorry, you stopped sharing.
Oh yeah. Let me reshare it. Oh. Yeah.
Oh yeah, I was wondering about the third point. Can you maybe tell me a little bit more about that one? The hardware acceleration, yeah, the FPGA and ASIC designs.
Yeah. So like so the task here is like to design some special hardware for some special purpose algorithms, such as the homomorphic encryption or the lattice-based encryption. Like we have a work in submission that's using some special hardware to do the polynomial multiplication. So in the software implementation, this polynomial multiplication are usually done by this NTT, and that's already fast enough. But the NTT, they have some like complicated access pattern that require you to access the memory many times, and that's not desirable for like so that part can be improved. Then we use a special hardware called this like RRAM or VRAM, so it can use the analog signal to do the polynomial multiplication way faster than the NTT and use less energy. So that's like one example of like how we can use some hardware to accelerate the lattice-based crypto. And the result we are getting is like maybe 1 or 2 order of magnitude faster than the FPGA design. So this FPGA design is already faster, maybe 1 or 2 order of magnitude faster than the software design. So we are like way faster than that and use less energy. So that's like one example. Like we can use FPGA or ASIC design to achieve better improvements.
Very cool. Thank you. Okay, I guess if there are any other questions, then thank you, Leo. Thank you for the great talk.
Thank you.
Yeah. Hope to see everyone else next week.
Yeah.